Welcome to the part 3 of the module 1 of this advanced prestressed concrete design course. So, in this module, we will be reviewing the short term and long term behavior of concrete materials, particularly what are the mechanical properties and what are the effect of short term and long term. And after going through this part, the student should be able to explain the basic mechanical properties of concrete and should be able to explain what is creep and what are the effects of creep on the long term behavior of concrete, and should be able to explain what is shrinkage, what are the different types of shrinkage and what their effects on the concrete. And we should also be able to discuss the various IS code provisions and how they can be used to quantify the effect of creep and shrinkage. Well, this is the overview of concrete properties. As you can see, we have short term properties and we have long term properties. Now, what are short term properties? So, this includes stress strain behavior of concrete, and we were using the material response, right. They do not change in short term, but in long term, depending upon how much time that you are looking at the particular mechanical property, they will vary over period of time, right. So, we will see what are the actual stress strain curve behavior of concrete, including normal strength concrete and high strength concrete, and then how the IS codes are actually coming up with design stress strain curves. We will use both IS 456 as well as IRC provisions and see how they actually deal with design stress strain curve behavior for concrete of different strength. Then we will get into long term properties of concrete that talks about creep. We will define what is creep and why is it important to understand the effect of creep and what are the mechanisms of the creep. Then we will also spend some time on shrinkage. And shrinkage, we have in fact three types of shrinkage. One is a drying shrinkage, another one is an autogenous shrinkage due to the chemical reaction, and then we also have carbonation shrinkage that typically is lesser. So, it is not explicitly considered in design unless your structural elements are located in CO2 rich environment, then we need to account for that as well. Then we will also see what are the effect of temperature on the mechanical properties of concrete. Right. So, let us move on to the short term properties. As you can see, the fundamental property that what we need for our design is the compressive strength. And as we have seen in the first part of the module itself, the F prime C is the cylinder compressive strength. It is the cylinder compressive strength. Okay. It is not the cube compressive strength, it is a cylinder compressive strength, right. So, this is the true representation of material property, concrete material. That is why, but you can also test cube, but then there should be a correlation that should be used. So, this starts with F prime C, which is the maximum strength that particular concrete can take, and F prime C stands for cylinder strength, as we have said. Okay, so it is a cylinder strength. And then elastic modulus is given by U, and maximum ultimate strain is given by your epsilon U. Okay. Now, we will typically this maximum ultimate strain is defined in the post peak behavior. For example, this curve that what you take, right, this is your post peak behavior, right. This is the overall stress strain curve behavior of a concrete cylinder, maybe it is a 90 megapascal grade cylinder strength concrete, right. Now, what is maximum ultimate strain? Typically, we take when the load drops more than roughly about, let us say, about 25 to 30% from the peak. So, this is your peak. You can either take 20 or 25 or 30, typically 20% or 25% is taken as a standard. So, you choose a strain at which the stress drops by about 20%, that you call that strain corresponding to that drop in stress is what we call that as an ultimate strain. It could be 20, it could be 25, 30 depending upon how you define it, but typically we take 20 or 25. Okay. And this the stress strain curve, this is how we get, and when we plot it, and you can clearly see here that this is for different grades of concrete. For example, this is for 20 megapascal and this is for 45, let's say, and this is for 90. So what you see here is as the strength of the concrete is increasing, right, your elastic modulus increases. Elastic modulus is the slope of stress strain curve in the initial region, right. So you take the slope, the stress divided by strain gives you elastic modulus, and typically we take at about 30% of your F prime C, which is your peak strength. At that point, we try to calculate the slope, then we define that as the elastic modulus. There are different ways of defining the elastic modulus, secant modulus, initial tangent modulus, so different varieties are there. But typically, when you take a 30% and you calculate your secant modulus, that is considered to be your definition for your elastic modulus in concrete design. So, but what you can see here is as the strength of the concrete is increasing, and this is the strain, if you look at all this point, these are the strain or these are the peak strength of all this concrete, right. So, as the strength of the concrete is increasing, so what you can see here is the strain corresponding to the peak strength of the concrete is also increasing. Okay. So, epsilon prime C is what we call that as a peak strain. So, epsilon prime C is called that as strain corresponding to peak stress. Okay. That epsilon prime C keeps increasing as the strength of the concrete is increasing. Now, what is epsilon u? I said when the stress drops by 20-25%, we define that as your ultimate strain, which is your epsilon u. But that epsilon u, if you see, it is like this, right? Somewhere around like this. So, maybe this here. Okay. So, you see here the difference between epsilon u minus epsilon prime C, which is delta epsilon, if you call, this is a measure of ductility of your material. As you can see, the strength of the concrete is increasing. The difference between the ultimate strain and the peak strain is reducing. But if you take your 20 megapascal concrete, your epsilon prime C is 0.002, right. Now, I said 20%, right. So, you see here it can go as high as 0.004 is basically your epsilon u for 20 megapascal concrete. So, the difference is 0.002, but if you take the 90 megapascal concrete, your peak strain is about 0.003, but your ultimate strain, this probably it will be around 0.0035. So, you can see here the difference for epsilon u and epsilon prime C for a 90 megapascal concrete is only 0.0005, but it is almost 0.002 for a 20 megapascal concrete. So, the lesser the delta epsilon, lower is your ductility of the material. So, concrete we know that it is a brittle material, but if you have higher delta epsilon, that means that concrete is not going to fail in all of a sudden. Okay. It is going to give you some warning and some plastic deformation before it can fail completely, right. So, this is very important. So, because why is it important is again prestressed concrete, we tend to use high strength concrete. So, for prestressed concrete, if you are using high strength concrete, then the ductility of the system can be compromised to an extent. So, that factor we have to keep in mind, at least from the concrete material point of view. Of course, you can deal with ductility by designing the reinforcement in a proper way, but as a material point of view, because we tend to use high strength concrete, that high strength concrete can fail in a more brittle manner than the normal strength concrete. Now, we have also, if you look at my previous lecture videos in advanced reinforced concrete, we have spent quite a bit of time on understanding the difference between cube strength and cylinder strength. The cylinder strength is a true material property, but due to simplicity, we start using 6-inch cubes, which is a 150 mm cube for determining the concrete compressive strength. But there are some plate and restraint effects. So, there is a confinement effect that comes. The cubes tend to be 25% higher in strength compared to cylinder. So, that is the reason we say if I have a cube strength, I have to multiply by 0.8 to get cylinder strength, right. So, and these are the different failure modes and so on. So, the important aspect is these are all short term properties. So, when I load the cylinder, typically we take about 3 to 5 minutes for completing the testing once everything setup is ready, the loading time. So, this is a very small duration of loading time within which we derive the mechanical properties. This is why it is called as short term mechanical properties, right. So, one thing is the higher the strength of the concrete, higher will be elastic modulus, but the brittleness is going to exceed because the difference between epsilon u and epsilon prime c is going to reduce, right. Now, we have models like parabolic model developed by Hognestad that is typically used in design for normal strength concrete. But Thorenfeld, he developed a very unified stress strain curve model for different types of concrete. So, this is again the stress strain curve for concrete. You can see this FC and epsilon c, and you have a red color curve which is typically high strength concrete, and this is blue color curve is for a normal strength concrete. This stress strain curve equation is applicable for all strength of concrete up to 100 megapascal, right. So, what are these things? This is FC is the stress in the concrete for any strain epsilon c, right. Now, F prime c is typically given to us, right. F prime c is given to us. This is your material strength, right. Now, I want to have a stress strain relationship that I can readily use in my calculations, right. So, F prime c will be given to you input property. Similarly, epsilon prime c can be estimated from your F prime c, and n and k have to be defined. If people are given this epsilon prime c, n and k and F prime c, then we can have an equation that is connecting Fc and epsilon c. And now let us see how to define this. F prime c, I test a cylinder and then get the value, right. So, that is given to you depending upon my target compressive strength what I design. I test some cylinders, I get my F prime c, right. But then other parameters like epsilon prime c, n and k have to be defined. Now, let us look at how they are defined, where n is a factor that accounts for curve fitting. So, what is a curve fitting? Okay, how the shape of the stress strain curve in this region, how it is changing from linear to non-linear, that is a curve factor. And k is a factor that accounts for how steep this particular post peak behavior is there, whether it is going like this or this or this is given by the k factor. So, it talks about post peak decay in strength, how fast it is decaying in its strength. So, these are the two parameters. Now, let us see. I told you we have to determine n, k and epsilon prime c. Now, what is n? N, as I told you, it is a factor that accounts for how it is changing from linear portion to non-linear portion. So, that has been defined in terms of this equation, which tells you what is EC. EC is your tangent modulus, and E prime C is your secant modulus at peak strength. So, what is the secant modulus? Again, we have discussed this, right. So, this, if you look at, this is the point, then if you connect from origin, if you connect from your origin to this is nothing but your secant modulus. Now, what is EC? It is a tangent modulus. So, what is a tangent modulus? So, tangent modulus is if I draw tangent to at the initial portion. So, this is going to be my tangent modulus, right. So, okay. So, this is nothing but your EC. So, this is E prime C, okay. This is E prime C, right. So, secant modulus is going to be lesser than that of tangent modulus. So, using that we can see how that factor is accounted, n factor, right. That again can be defined in terms of f prime c. There has been a lot of experiments have been done and then the equation has been derived. Similarly, as we have seen that epsilon prime c from the last slide, we say that higher the strength of the concrete, epsilon prime c also increases to an extent. But how much it increase, that is again function of your strength of the concrete, right. So, that is again can be defined in terms of your f prime c or fck. So, again fck is a characteristic strength of the concrete as per IS code. Then we also have a relationship between cube and cylinder. So, f prime c and fck can also be related. So, this is the equation for your epsilon prime c, right. Now, what is k factor? When I am using this equation, I take k equal to 1 when the stress is less than f prime c, or in other words, when the strain is an independent variable, I keep varying the epsilon c and then I calculate what is stress. When epsilon c is less than epsilon prime c, now once I find n and I am given f prime c, I can calculate epsilon prime c. So, I know what is the epsilon prime c and I know what is n, and k I take it equal to 1 when epsilon c is less than epsilon prime c, and then k will be taken more than 1 when epsilon c becomes more than epsilon prime c. For example, we said f prime c equal to 20 megapascal. We saw that epsilon prime c is 0.002, right. So, this is fixed. Once f prime c is fixed, 0.02 is fixed. Similarly, I can also get my n value, right, from this equation. So, once everything I know, I plug into this equation, then I can derive a relationship between stress and strain. So, that is how we get this particular curve, okay. For example, this curve can be got. This is your material curve, okay, stress strain curve. So, this is the way we get it. In EC also, the tangent modulus is also, expressions have been already developed, which is based on the strength of the concrete and also the density of the concrete. Nowadays, people also use lightweight aggregate. So, your WC, which is basically the unit weight of concrete, which is given in kilogram per meter cube. Depending upon your density of your concrete, you can put it in that equation and you get your EC value. So, if you substitute everything for EC, then you finally end up with this kind of an equation. EC is this, right. So, substitute in this equation, then you get your formula like this. So, EC is known, E prime C is known, epsilon prime C is known, N is known, K is known. So, I can get the red color curve that we are talking about, which is the stress strain curve. Okay, now let us see, this is the actual material property. When I test it in a lab, I mean this kind of stress strain curve that I get, that is typically used for research purposes to see, to calculate the behavior and come up with estimations of whether theoretical calculations are matching with experimental results. Now, for design purposes, I cannot use the actual property that I am getting it from testing, right. I have to reduce it by applying some factor of safety, because you have to account for the variability in the material properties. So, that is why codes come up with design stress strain curves. Now, let us see what are the design stress strain curves. Again, in the advanced reinforced concrete design course, we have spent quite a bit of time on defining what is characteristic strength and so on, right. So, IS code defines this curve as a characteristic curve. Now, what is a characteristic curve? So, this is your design, the characteristic curve, that what we have, right. Now, characteristic curve itself, we say that it is a 5 percentile strength, 5 percentile strength, right. It is a 5% strength. That means only 5% of the samples are expected to fail, right. So, we have defined what is the characteristic strength from the normal distribution, from the frequency distribution of the sample strength. Then we have defined what is FCK. So, only we choose a value so that only 5% of the samples will be less than that particular value, right. So, now that is your FCK. Now, that FCK is also knocked down by a factor called 0.8 times 0.85, which will work out to be 0.67. Okay. Now, why is it 0.8 and 0.85? We have said because the strength what I am getting it is from cube, the actual material property should be cylinder. So, I need to multiply by 0.8. Now, then there is why one more this 0.85 is coming, that is coming from to account for the size effect, because we test typically small elements, but actual structural elements are high, and when you cast concrete there is also always tendency of more defects in a larger system. So, to account for all those things, the code is saying that you knock it down by another 15%. That is how we get this 0.67 FCK for characteristic curve. Now, this also I cannot use because again there will be lot of variations in my material property. Code wants to be absolutely sure. So, what we do? We divide this by gamma m to get this. So, gamma m is 1.5. So, that is the reason 0.67 FCK by 1.5 will give 0.447 FCK. So, you get this design curve. That is how we get your design curve. So, this is the equation for your design curve, and this is a typical parabolic model. Okay. So, typical parabolic model is this. Okay. And as I have told you, the Thorenfeld model is more generic, but the simpler version is your parabolic model. Parabolic model, and usually it is used when concrete strength is less than 40 megapascal. The moment you go for higher strength concrete, this parabolic model will not do a good job in actually representing the stress strain curve. So, we have to use other good models like Thorenfeld model. That is the reason. And in fact, in concrete, in prestressed concrete, typically we use strength more than 30 megapascal, as you all know. Post tension, the minimum strength is 30. In pre tension, the minimum strength we use is 40 megapascal. So, we tend to go into the high strength concrete categories. So, that is the reason Thorenfeld model is more applicable for modeling the high strength concrete. And you can see this is the parabolic equation. So, the shape, when the strain is less than 0.002, my stress can be given by 0.447 FCK times 2 into epsilon c by epsilon prime c, and typically this is epsilon prime c. For again for concrete strength less than 40 megapascal, I can take epsilon prime c equal to 0.00. And as you can see from the first curve also, epsilon prime c does not increase much up to 40 megapascal. It is very close to 0.00. So, for simplicity, for any concrete strength less than 40 megapascal, we always take epsilon prime c as 0.00. Then after this it is a parabolic, and after that it remains constant, right. So, that constant value is kept as 0.447 FCK. Actually, this is for the design stress strain curve, right. Okay. So, this is your epsilon prime c, which is 0.002. So, that is this, right. So, anything above this, it remains constant at 0.447 FCK. So, that is what we have taken here. So, this is the design stress strain curve. IS code is specified. Okay. Now, let us see what the IRC 112 specifies. It is also exactly same type of curve, which is a parabolic curve, and they call this as FCD, which is a design curve. Now, what is FCD? FCD is nothing but design curve, right, which is alpha FCK by gamma m. Okay, that is what they define here. Now, what is alpha? 0.67. That is exactly same as that what is given in IS 456, right. So, FCD is nothing but 0.447 FCK again, because this 0.447, how it is come? 0.67 divided by gamma m, which is 1.5 again, right. So that's how we end up with this design stress strain curve, and this is also again a parabolic equation, and then the stress will remain FCD, the stress will remain FCD, which is 0.447 FCK for any strain values which are higher than peak strain. Now IRC code is defining your strain, peak strain as epsilon C2. It is taken as epsilon C2, right? And similarly, the ultimate strain is taken as epsilon CU2. Now, the IRC code gives you different simplifications. You can either model it as a parabolic and straight or linear and straight. So, different simplifications it is allowing. But now for this, I am just trying to tell you that both are same. Only the constitutive equation will slightly change, but the overall nature of these equations are one and the same. And again, gamma m is kept constant as 1.5 in IS 456 or IS 1343 as 1.5. However, in IRC code, it takes 1.5 as a material safety factor for basic and seismic combination, and because mostly it is for use for bridge applications, during construction stage you may also have an accidental loading combination which will be of very temporary nature. So, when you do analysis for such kind of temporary loading, then you can reduce the material safety factor to 1.2, which the IRC code is allowing. But however, IS 456 or IS 1343 does not take into account that gamma m is always taken as 1.5 here, right? But here gamma m can be two different values depending upon what kind of analysis you are doing for what kind of loading, right? Now, so this is the table that is given in IRC 112, as you can see here, and this is your characteristic strength of concrete, cube strength, and this is your mean strength. FCM stands for mean strength, and you know that the mean strength has to be higher than characteristic strength, because characteristic strength is a lower bound where only 5% of the samples are expected to go below that, right? 95% of the results are expected to be above the character. So, but that's the reason the mean strength is expected to be higher than your characteristic strength. And this FCTM is basically the mean tensile strength. T stands for tension. So, and then again this is again characteristic strength, and FCTM is the mean strength, sorry. And then for 5% characteristic strength, you get 1.1. If it is 95% and this has to be greater than the mean, as you know. From your normal distributions, you know that if you put the values strength, right, in the x-axis, and then here, you know, number of samples, values at what you are getting, right. So, typically you get this normal distribution, and you know, and this is what we take that as mean, and this is your 5% sample, and this is your 95% value. So, 95% value should be higher than your mean strength, and 5% strength has to be lower than that. So, that you know from the bell shaped curve you can find out what should be the coefficients for different percentile strength, you know that. And these are your actual material properties defined by IRC 112, but what we use is this particular values, which is epsilon C2 and epsilon CU2, okay. And as you can see here, up to 60 megapascal, the code has kept peak strain as only 2. This also 2, I have to divide it by 1000. So, this symbol dot by this indicates that this value has to be divided by 1000, right. So, that is why 2 divided by 1000 is nothing but 0.00, that is exactly the same value epsilon prime C that we have taken it as 0.002. I told you it is strictly 0.002 is valid only up to 40, but the code has made it simple. Even up to 60, the code is allowing us to use 0.002 as a peak strain for design. Similarly, epsilon CU2 you can see here, it is taking it as 0.0035, that is your failure strain, ultimate strain that the code is asking you. But the moment you go more than 60 megapascal, the code is saying that again epsilon C2 is increasing, and you can see here epsilon Cu2, the ultimate strain is reducing. That is exactly what we saw in the actual stress strain curve behavior. And now this n is basically an exponent that is going to see the shape of the curve, and if it is true, it is a parabolic equation, and up to 60 megapascal the IRC code is asking you to use parabolic equation, and then the exponent value keeps reducing, similar to what we have for Thorenfeld's model. And these values are actually for linear assumption. So we have different types. This is for somewhat parabolic, we can say, stress strain curve, and this is for some simple bilinear approximation of your stress strain curve. So IRC code is more elaborate and gives you different options for the designer to use simplified stress strain relationship or the parabolic and straight relationship, right. Now this is the grades of concrete, and for prestress, as you know, IS 1343 is the code, and you can see here that these are the different grades of concrete strength that are allowed by IS 1343, starting from M30. The minimum in a prestress concrete, minimum strength what we need to use M30, and IS 1343 allows you to go up to M80. Of course, you can go for a higher grades also, but then the provisions that are given in the IS codes are applicable only for this range of concrete strength. Okay. In fact, the code also says you for concrete grade greater than 60, design parameters should be evaluated from specialized literature or experiments. So the code is very explicitly stating that this is only will give you conservative correct estimates only up to strength of 60, but more than 60 you have to look at specialized literature. Now for IRC 112, you can see there are different grades of concrete that have been given, and these are your ordinary concrete based on your nominal mix proportions. Okay. Okay, and then we have standard concrete. You do your proper mix design, and you can go from M15 to M50, and then you have high performance concrete. Now, what is high performance concrete? Again, you can also look at my previous videos in NPTEL course on advanced reinforced concrete design. We spend a lot of time. We try to improve the durability of the concrete by using supplementary cementitious materials like fly ash, slag, and so on, right. So when you carefully design the mix, you develop a dense microstructure and you end up with a better durable concrete. So the strength can be same, but by adding the supplementary cementitious material, then I can get more durable concrete. So that is what designated as high performance concrete, starting from M30 to as high as M90. So the provisions in IRC 112 are valid for strength up to M90.